questions from yesterday? So we begin. So yesterday we were analyzing a 4-point function, and what we had shown is that the usual expression for the 4-point function, where you fix 3 points and then integrate over the 4th one, we could manipulate and write it in a somewhat more symmetric form. And the symmetric form had the following structure: you had a 1 over 2 pi, which is a normalization, which, as I said, don't worry about this too much now. Later on we will fix all the signs and normalizations properly. So we had d2 lambda Z1 here stands for both Z1 and Z1 bound, because these are clearly dependent on both homomorphic and anti-homomorphic coordinates.
These integrals that you introduce, these are just zero modes, right?
Yeah, these will be zero modes. Yeah. Right now I'm just writing it in this fashion. Because this is what we had arrived. We didn't introduce them as zero modes. We wrote it as an integral and then we picked up the contribution from the poles. Right? So that's, but eventually it will be identified as zero mode. Then you have C bar C, d3 of 0, and C bar C, 4 of lambda y.
So yesterday you wrote down those different modes BA in terms of the contributing one. There if you just put A equals to
Yeah, exactly. Then it will be like that.
Without performing the integral, the total host number is more than 6. Right?
Total host number is still 6 because there are 2 plus 2 plus 2 plus 2, 8 from here, but b and b bar gives you minus 2. Right? Because the total host number is still 6. If we didn't introduce this, then the total host number will not add up. Right? Okay. So what you want to do is to further manipulate this and see how to regulate the divergence. And the idea is that the initial divergence that we had started with, that's what corresponds to this Z4 going to 0. This in this language corresponds to lambda going to 0 divergence. Okay, because as lambda goes to 0, you can see that corresponds to these 2 points coming close to each other, right? And you have to understand how to regulate or how to deal with that divergence. So the first thing we'll do is to try to give an operator interpretation of this. So let's try to reinterpret this as a matrix element within vacuum. So this is vacuum expectation value. And inside the vacuum expectation value, you have radial ordering. But we will just assume that these are already radial ordered. Okay, namely mod Z1 is larger than mod Z2. Otherwise, I have to write radial ordering before this. So C bar C, you are at Z1. C bar C, D2 of Z2. Then now here by construction it's radially ordered because if you recall we have assumed that these contours are outside these, right? So in particular for small enough lambda these 2 points are both close to the origin. So all you have to do is that you have to take the circles of these integrals to run over radial circles. Okay, or no, not radial circles, circle of constant radius around the origin. And that radius has to be chosen in such a way that the radius is larger than these distances but smaller than mod Z1 and mod Z2.
Should not V3 move to the extreme right? Because
Yeah, V3, I have not written V3 yet. Right? In this language, it doesn't matter where you write, but when you write it as a radial order, V3 will move to the extreme right. So then we have C bar C, V4 of lambda Y4, and then C bar C, V3 of C, and then back. Okay, this radial ordering is arbitrary. I mean, you could have made mod Z larger than mod 0, you just extend the limits. Okay, so now what we will do is to reinterpret this. You see this, there is lambda dependence here. So what we will do is we will reinterpret this as lambda to the L0, lambda bar to the L0 bar, and remove the lambda from here. Okay, why? Because after all, this acts on the right. Okay, lambda to the L0 acting on the vacuum, of course, it gives you 1 because L0 analyzes the vacuum. Okay. So, we have to basically look at what happens as you move through these. These are dimension 0 pancakes. Okay, so there is no overall factor that it picks up, but as it moves through this, it scales y4 by lambda. Okay, that's what L0 lambda to the L0 does, right? It scales the coordinates by lambda. So as it moves through this, it will scale y4 by lambda, and it will scale 0 by lambda, but that of course is a 0 again. Okay, so nothing happens. So this is the same as what we had before, namely a lambda multiplied. Is this part clear? Okay, next what we will do is to insert a complete set of states in between. Okay, so we insert a complete set of states, let's say here, n, and insert another complete set of states in m. Okay, later on we will make more explicit what one means by a complete set of states, what are these n's, how they are normalized and so on. Okay. But right now just take this, that if you have a Hilbert space, right, you can always have a complete set of states and write the identity as in this fashion. Okay, later on we will try to make it more specific. And similarly here. So this I'll write this right now as 1 over 2 pi. So what we have done by this is that the lambda dependence where the integral is totally in the middle. Okay? You can see that neither the thing in the front nor the thing here depends on lambda. So the lambda integral in some sense can be done independently of what vortex operators you had started with. Right? You have made this factor a universal factor. Right? That doesn't directly depend on what vortex operator you started with. So I write this as 1 over 2 pi integral dt lambda over lambda bar. Let me write the lambda dependent part first. So n. Now what I will do is I will write this as b0 and b0 bar. Right? If you look at the definitions of b0, bn and bn bar that we gave last time, okay, you recognize that these are nothing but b0 and b0 bar. So n b0 bar, lambda to the L0, lambda bar to the L0 bar, m, and then you have 0 c bar c, d bar c bar, c bar c, d, n, and n.
there should be sum over m and n.
Yeah, so repeated indices are summed over. So this is the sum over n and m are understood. Is this okay? So let us now try to do this integral. So I'll do this integral by changing variables. So I'll write lambda e to the minus s minus I theta and lambda bar e to the minus s plus I theta. So d2 lambda over lambda lambda bar is essentially ds d theta. Okay, up to normalization. Again, normalization I'm not too worried about right now. Okay, there are factors of 2, etc. Calculate this. Is this okay? Yeah, because d lambda over lambda wedge d lambda bar over lambda bar. So that gives you ds plus I d theta wedge ds minus I d theta. And that gives you ds d theta. Okay, up to factors of I and 2, which are not given here. So then this integral can be written as integral ds d theta e to the power minus s minus I theta, which is integral ds d theta e to the minus s times n naught plus n naught bar e to the minus I theta times n naught minus n naught. Now note that so far I have not written anything about the range of S, because range of S and theta will depend on what range of lambda and lambda bar you want to integrate. And after all, lambda is related to S and theta by this. But what you know for sure is that this range that you want to include, that you want to have here, should include the region where lambda is close to 0. Yeah? Because that's the region you want to deal with. For the other regions, you didn't have to do this. Right? You could have used the original form of the integral, because the divergences come from the region where the arguments are extended. So lambda goes to 0 will correspond to s goes to infinity in this language. Right? So the s goes to infinity, it should certainly include. What else you include is up to you. Okay, the final result should depend on what you include. So what I'll do here is I'll do this integral from s naught to infinity, and the theta integral I'll take from 0 to 2 pi. Okay, theta is a periodic variable, so it's natural to take the theta integral from 0 to 2 pi. Okay, this includes the full region around lambda equal to 0. And now I define this. Okay, and this is where this analytic configuration comes over. I define this to be e to the minus s naught So what I have done here is that integral ds e to the minus s times L naught plus L naught bar. I can integrate. Right? I wrote e to the minus s naught times L naught plus L naught bar divided by this. Now in this I have assumed that the upper limit of integration is 1. So this gives you boundary terms, right? It's e to the minus s times L naught over L naught bar over L naught plus L naught bar. That's the indefinite integral, and you have to evaluate it between the two boundaries. I have assumed that the contribution from the upper boundary, s goes to infinity boundary, is 0. This would be true if L naught plus L naught bar is positive, then e to the minus s times L naught plus L naught bar is equal to 0. This will not be true if L naught plus L naught bar is negative or 0. However, this will be my definition. Okay, this is the way I try to define the integral. Okay. And this is precisely what one means by analytic continuation. Okay, we analytically continue the results as a function of L naught plus L naught bar from the region where L naught plus L naught bar is positive, and use that result even when L naught plus L naught bar is negative or 0. Is this point clear?
So the contact term the contribution is usually set to 0.
Yes, it is set to 0. The thing from x naught equal to infinity, that's it, but not contact term. That's more like you go to infinity extents. Right?
No, here is lambda exactly equal to 0.
Yeah, lambda is exactly equal to 0, right? So in terms of cubes, it's like becoming two spheres, right, connected by infinitely round cube. See, this S you can interpret as the length of a cube that is connecting the two spheres. Okay. So it is true that in the original z variable, it looks like the z is going to 0. 2 points are coming close.
V3 and V4.
Yeah, V3 and V4. But in this language, V3 and V4 are never coming close because they are already at fixed separation. Right? Two spheres on the first sphere, these are at fixed separation. On this sphere, these are at fixed separation. There is other term. Here, not here. Here Z1, Z2 are fixed. Y4 and 0 are fixed. Right? So what is going to infinity? So in the limit, when initially the 2 points are coming close to each other, right? The interpretation is now that it's like two spheres connected by infinity long cube. Okay, and boundary term that could possibly come from the other end, okay, the infinitely round cube, that is set to 0.
So, I mean, when I'm encountering that there might be a similarity, I'm setting that to 0 by definition.
Yes, by definition. That will be the definition of my integral. And this is precisely what one means by analytic continuation. Right? If you look at the original, go back to the original way one defines it, right? When there is an analytic expression, right? You will find that basically amounts to doing this.
So then how will I check my consistency whether this what I have done is correct?
Yeah, so you have to now make sure that the whole result is independent of x naught, for example. How you cut off, right?
It's not.
Yeah. This region, you could change x naught, right? And this will change. Right? At the same time, the integration region that is left out will also change. Right? And the sum total must be independent of x naught. Right? Even though here we are defining the integral not as an integral but as a sum, like this. Okay. So in other words, whenever 2 points are coming very close to each other, right, we reparameterize them in this fashion, okay, and reinterpret the integral. You don't write it as an integral, you write it as sum over n and m, okay, of this form. Okay, so I'll write down the sum explicitly and then it will become clearer. So then the amplitude becomes the following form: 1 over 2 pi n b0 naught 1 over del 0 plus del 0 naught. Oh, I should have said something else also. So 2 pi gets cancelled. Okay. Okay. Here the theta integral, right, I have written as delta L0 L0 bar, right, and this is written, okay, based on the knowledge that L0 minus L0 bar eigenvalue in a good conformal field theory is always integer. Okay. So L0 minus L0 is integer. Okay. So when you integrate it to the minus I theta times an integer from 0 to 2 pi, right? It's 0 for any non-zero integer n, but it's 2 pi for n is 0. Right? That's what is given.
It's like delta function.
Yeah, it's like a chronic delta function. But if for example L0 minus L0 bar had half integer values, right, this would not be true. Okay, so it's only if L0 minus L0 bar is integer, okay, that this is true. And this is true in boson extent theory. So delta L0, L0 bar M, and then you have 0 C bar C Z1 Z1 C bar C Z2 Z2 M and M C bar C.
Sorry, why don't you have the E3 minus S naught P?
E to the minus?
It's not.
Yeah, it will have. E to the minus is not. L0.
When you introduce this complete set, we have not assumed that whether these states have host number 2 or more.
No, except that unless it has the correct host number, the result will be 0 automatically. Right? So right now we are summing over all possible host number. As I said, later on we will try to make it clear how to construct this such complete states. Okay, right now I am not assuming anything about host number, but you can clearly see, right, that from this it clear that unless A has host number 2, it will vanish. Okay, now let's look at the structure of this a little bit. Okay, first of all, okay, so you can always choose A and M to be L0 and L0 bar eigenstates. Right? You can always choose the basis of states which are eigenstates of L0 and L0 bar. Okay, in a control filter you can always do that. In that case, this it need not be diagonal because at the same L0 and L0 bar eigenvalue there will be multiple states N and M. Okay. But at least it will be block diagonal. Okay, and in any block will be characterized by the same L0 and L0 bar eigenvalues. Yes, it will have a block diagonal form. Okay. And in that block, okay, in a given block, so a given block has L0 as k square by 4 plus some, let's call it Cn, and L0 bar also k square by 4 plus Cn. Why the same Cn? That's because of this constraint. Right? Unless L0 and L0 bar are the same on two sides, okay, of course the matrix element vanishes. So it's the same Cn. What is Cn? Cn is some discrete value, right? If it's free bosonic string theory, then Cn's are created by they are the oscillator elements. Right? So k square by 4 is the contribution for the momentum factor. Okay? L0 and L0 bar contribution. Okay, if you take a partial operator equal to ik dot x times some operator, equal to ik dot x contribution is given by this k square by 4 on the two sides. Okay? Whatever else, the oscillator, that's discrete. That's what I am calling by Cn. So in that case, the first factor, this factor, 1 over 2 pi is 100, right? Because the 2 pi factor from there. So this factor becomes e to the minus s naught times k square by 2 plus 2 Cn times 1 over k square by 2. Is 2 over k square plus 2 Cn times some constant matrix which I call AMA. Some finite constant matrix. So this is one block. Okay, this finite dimensional matrix comes because in a given for a given L0 and L0 bar eigenvalues, there are only finite number of states. Okay, that's this matrix AMN that comes from.
Block diagonal, won't that V0 P0 bar be a problem?
No, V0 bar commutes to the L0 L0 bar, right?
Okay.
So they don't change the L0 eigenvalues.
Sorry, what is the definition of a block? It is
A block is defined by taking states from the same L0 and L0 bar eigenvalue.
okay.
In that way, calculate the matrix element, right? And then the next block will have a different L0 and L0 bar eigenvalue and so on, right? So in a given block, the L0 and L0 bar dependence factors I have explicitly written down. These are just some operators whose matrix element has to be computed in a given block. And now you see that this factor over here has the interpret, it looks like 1 over k square plus m square. Yeah? This is like the mass square of the system. So this looks like what we'll get from a propagator. So if we had a Feynman diagram of this form, right? We are calculating after all a 4-point scattering, right? Imagine that we had a 4-point scattering of 1, 2, and 3, 4. So here there is a Feynman diagram of this kind.
So should we get a square plus 4c?
K square plus 4c. Then the interpretation of this factor over here, okay, at least this factor over here, is like you have some state propagating here, okay, a state of states propagating here, whose propagator is factor is given by 1 over k square plus 4cn. Now what about this? Okay, this is something that you don't normally see in the Feynman propagator. So it's most natural to include this in the vortex factors. Right? You take half of this, okay, square root of this and put it here, and square root of this and put it here. So the vortices, these individual vortices, will be these matrix elements: 0, C bar C, B1, Z1, C bar C, B2, Z2, N. Okay, so this end is N, this end is N. A, Mn is basically the propagator. Okay, so the propagator is not diagonal, there is an AMN factor sitting there. And then when you impose this, we include half of that, it will be minus half S naught A square by 2 plus 2Cn in one of them. And similarly, this vortex will be given by M C bar C V4 Y4 C bar C times then set time.
The Amen is due to the B naught bar.
Yeah, B naught, exactly. Amen is because of the B naught part and so on.
What is the Cn? Any oscillator contribution from the N state, right?
Yes, that's right. Any oscillator contribution from the states. In a given block, right, all of them have the same L0 and L0 bar eigenvalue, but there were different oscillator combinations to the same L0 and L0 bar eigenvalue. Right? So Cn is basically the contribution from the oscillators. Okay. So the idea is that we think of this part of the contribution, okay, that you get by integrating from S naught to infinity, not as an integral, but as a sum of this kind. Okay, this sum of course also for infinite number of states, because there are infinite number of intermediate states propagating. Right? So one may worry whether this sum is convergent, right? Otherwise you will again run into a problem of divergences. Okay? But one can argue that for sufficiently large S naught at least, this sum is indeed convergent. Okay, one way to see the other way. This is just a quick counting. If we try to see the convergence, the number of states grows typically as exponential of some constant times square root of Cn. Okay, this is a Hagedorn growth. Okay, as L0 increases the number of states grows as square root of Cn. But this exponential separation e to the minus x naught Cn basically makes this converge. Or sufficiently large x naught. Right, where this is exponential surface and this is much more surface than the rate at which this is going.
Was it the base number worked out for the AN?
Yeah, so basically, you can work out the host number. Again, that I'll do this very carefully later. You can say that n must have host number 2 from here, right? Similarly, from here, n must have host number 2. But if n has host number 2, then the conjugate has to have host number 4. Because the inner product is non-zero only if host number 2 is paired with host number 4. Okay? So this is host number 4, this is host number 4. Okay? And these are host number minus 2. So that's the way the host number adds up to 6. In each term. So in each term, host number adds up to 6.
Okay, so this inner product is not the BPZ inner product.
Well, this is, you can say BPZ inner product. This conjugate is not BPZ conjugate.
And not the BPZ.
Yeah, it is not a BPZ. That's why I said that I'm not being careful about what this means, right? It's just a complete set of states. In the most naive sense that you can think of in any Hilbert space, you can insert a complete set of states. But later on, we'll define more carefully, okay, the definition of the BPZ inner product and also see how to define these. Is this point clear? Okay, so this is the way we will try to interpret the divergent contribution. Okay, that if you think of it this way, then there is no divergence from this region. Okay, and if you want to do write a computer program to do calculation of the 4-point function, okay, you just instruct it that whenever say Z4 comes within a certain radius of Z3, you don't integrate, instead replace it by sum of this guy. And you do the same thing for Z4 near Z1 and Z4 near Z2. Right? And those will have interpretation exactly in the same way as Feynman diagrams of a defined time. Yes.
Here it seems that the need for this analytic continuation, it depends on the spectrum, because values of L naught and L naught bar, that was problematic,
Yes.
would have been problematic. In the original case, how do we see that it's a spectrum that may create problem?
This is the intermediate state, right? In original case also the operator product. Basically, why do you get divergence, right? You do an operator product expansion, right? And the Z dependence depends on the dimension of the operator that is appearing on the right hand side.
Yes.
Okay? And that operator that is appearing on the right hand side is precisely this thing that is flowing through here. Okay? So this is, so what we are doing essentially in this is that we have expanded in operator product expansion. Okay? And so that you have a power series in Z, and then we are explicitly making the analytic continuation for each power. Right? And so if the power is positive, then you don't have to do anything. Right? Integral Z to the alpha is integral. Right? If the power is negative, right, we define it by analytic continuation. And the reason that how we analytically continue, okay, that how you regularize this integral is independent of what you started with, is because the intermediate states which are flowing are universal. Instead of all states which are flowing. Right? The precise coefficient of the operator expansion doesn't really matter because those are in these 3-point functions. Okay? what matters is what is flowing in the intermediate state. Okay, and that's what we see here. So the what is flowing in intermediate state, that information is here. Okay, so as I was saying, the other terms have an interpretation of this kind. And after you have isolated these regions, okay, each of which has a Feynman diagram interpretation of this kind, or this kind, or this kind, you are still left with a region from where there is no divergence. Right? Because in the Z4 integral, what you have done is you have cut out some region around Z1, some region around Z2, and some region around Z3, and given them interpretation as these kind of Feynman diagrams. But then there is a region which is away from Z1, Z2, and Z3, right, which still has to be integrated over. So how do you interpret that contribution? So that contribution, you just think of this as a Feynman diagram like this. So no divergence, right? It's a 4-point function. We just think of this as contribution to a diagram like this. Okay. And the integration over Z4 is included as part of the definition of this 4-point function, of this 4-point vortex. Is this part clear?
Like there is not been any kind of a perturbating expansion. Like in QFT we see like this is kind leading term, this is like second order in vortex.
Well, the point is this will be order G square. This vortex will be of order G square. So this perturbation expansion, because after all of it is coming from the 4-point function, right? So you try to assign vortices, the actual powers of coupling constant, right? You will find a 3-point function is of order G, 4-point function is of order G square. This is what happens in Young-Wade theory, for example, right? So the power of the couplings will work out by construction, because after all it's the same 4-point function, right, which you have divided up into different regions. So they must come with the same power G. Now of course this is, we have not derived it from field theory. Okay? This is just I am trying to give an intuitive picture of why we expect that there should be a field theory kind of interpretation for these 4-point functions. Okay? And why it is useful? Because in a field theory, the fact that this is 1 over k square plus m square is automatic, right? You don't need any regularizer or anything. By definition, it's 1 over k square plus m square, the propagator. Okay? But if we had started with this integral, okay, there we needed some kind of analytic continuation, right? To show that, to conclude that we have a 1 over L0 plus L0 bar, okay, or this. This is not strictly equal to the original integral we started with, which was divergent anyway. Okay? This, you have to make an analytic continuation to define the original integral to be this. But if we have started from field theory and drawn these Feynman diagrams, you will have never seen the original integral, right? You will only see these. Okay, so there will be nothing to regulate. Okay. So another way of saying this is that if we start with a field theory which has a propagator,
So you were saying that A0 shouldn't come in the total language to calculate all these 3 contributions and this 4th one.
yes, some
That will have no A0 dependent.
that will have no S0 dependence, exactly. So the sum of the 4 contributions should have no S0 dependence.
Here the A0 dependence is like e to the power minus A0 by 2. If we keep adding up, it will stay there.
But the 4-point function has an S0 dependence because 4-point function, okay, will be integrated over a region that has been removed from the original integral, right? So that boundary,
type of term that we can say.
exactly. So it will have an explicit subtraction terms, right, which will cancel this S0 dependent terms over here.
Each of these will have their own S0. I mean, in principle. Or
Yes, each of them can have their own S0.
This will be dependent on, say, 3 S0s, the 4-point.
Yes, a priori. But the point is that, I mean, eventually, if you really want to get it from a field theory, right, then these vertex and these vertex and this vertex must be the same vertex. Right? So you cannot really have defined S zeros for each. Right? There will be defined S zeros, but that should be related. Okay? Otherwise, you are using one kind of vertex for this diagram, another kind of vertex for this diagram, which you can do for regularization, but that's not a field theory, right? So you will see that when I construct a field theory, it will be all related. And there will still be a parameter, right? Because field theory is not unique, right? You can take part of this, and part of this, and include in the definition of the 4-part function. Okay? So you can change the 3-part function and 4-part function accordingly. So the total answer is still the same. But it's not completely independent vertices that you're using. Right? Otherwise it will not have a field theory.
I mean, in the case of the fourth diagram,
Yes.
if we integrate, that will be from S0 up to the rest of the space, because
That's it, yes.
for the first
Yeah. Well, there of course you will not use the language of S, right? You will use the language of Z4. But whatever S equal to S0 corresponds to some cutoff on Z4. Right? It will be outside that region, right? You will not go Z4 closer to so Z4 around Z1 region will have to be cut off. Right? Yeah. And the point is that even though we are treating this differently, right? Here we are really having sums. Yeah? Because if you try to write as an integral, you get divergent. Right? Here you really have an integral. Nevertheless, when you add up the 4 contributions, the result will be independent of S0.
So you said if you have started with the field theory, we will never see this divergence.
Yes. So I'm just explaining why, how this divergence comes. So in a field theory, what are you doing, right? So in a field theory, you often have propagators, right? Either in the loop or in the tree. Yeah? The internal propagators are always there. And one thing you often do in field theory is to use Schwinger parameterization. Right? For many purposes, you write this as integral 0 to infinity e to the minus s times k square plus n square. But this parameterization is not valid if k square plus n square is negative. Right? So, from a field theory perspective, the reason that we had an original divergence was because we are using a Schwinger parameterization for a propagator for which Schwinger parameterization is not valid. So, from the field theory perspective, these divergences that we had seen are fake divergences. Okay? They are arising because you are doing something wrong. Okay, you shouldn't simply use this Schwinger parameterization if k square plus m square is negative. And that is the reason why, from the field theory perspective, you never see these divergences. Is this? Yeah. Okay, but field theory actually can do much more. Okay, if we really have a field theory interpretation. So let me just mention one. You see, we had this 1 over k square plus 4c, right? These kind of divergence. Okay? And k, of course, is fixed by the external momentum in this case, right? Because we are taking 3 and 4 to be close to each other, right? So k, which is the momentum that is flowing through this, right? That's just k3 plus k4. Okay, yeah, right? I mean, in terms of this vortex, k was the momentum carried by n, right? Or momentum carried by n. But momentum conservation tells us that is the same as the sum of the momentum carried by these two vortices, k1 plus k2, which is also the same as sum of the momentum carried by the other two vortices, k3 plus k4. Okay. So k square is k3 plus k4. Okay. And this one is of course not divergent when for a generic k square. Okay. Even when the original integral was happening. The original integral was divergent whenever this combination was negative. Now it's not divergent when this combination is negative. But it has a divergence. It has divergence of k square is minus 4c. This divergence you cannot get rid of, either in field theory or in string theory. Right? The analytically continued result that you get in string theory, okay, is not doesn't have the usual divergences, but it has divergence whenever k square is minus 4c. Okay? And that divergence is also there in field theory. So what is the interpretation of this divergence? Okay. This divergence basically is the same divergence that you see when in field theory you sit on the pole. Okay. You have external states A of q1 plus k2 whole square. When this can produce a particle of mass mn, okay, you expect a divergence because there is 1 over q1 plus k2 whole square minus mn square. Okay. That is this divergence. Now, if you are doing string theory, then it is very hard to get rid of this divergence ever. Okay, you will always have this divergence because it's there at tree level, okay, and you don't know what to do with it. In field theory, however, you know that there is a cure for this. The cure in field theory is that once you start doing loop calculations, the masses will get renormalized, okay, and they will in fact, in particular, become an imaginary part. Okay. So, because this occurs when it can actually produce particles, Cn will become, in field theory, Cn will become complex under loop conditions. But to see this, we have to use some trick which is of course standard in field theory. But what you have to do is that you have to basically sum over the infinite number of 1p items, right? Okay, because only after you sum over all this, right, that you will see this as 1 over k square plus m square plus sigma, okay, plus something which basically shifts m square. Yeah, and in particular, this something has a imaginary part which shifts this thing away from the pole. Okay. So in field theory, you know how to cure it. Okay, but that cure requires that you have to identify a certain class of diagrams and sum over infinite number of them. But if you are using the standard conventional on-shell string theory, okay, there is no way to make common diagrams like this. Okay, because in theory at one loop you will get one diagram, right? It's not that the diagram can be decomposed into the different 1pi parts and sum over. So field theory is useful, okay, not only to understand the value of the analytic continuation, which in principle you could have done also in string theory, at least in simple cases. But field theory is useful also to understand how to cure the divergences.
If x square is 0, still is there a imaginary part which comes up?
Where?
If m square is 0, because then the particle will, massless particle will decay, right?
Yeah, massless particle will decay, but in that case, you will never really see that k square equal to m square. Because if you take two particles and collide, right, their k square is always larger than 0. Right? Except when they are soft. Right? When you take the external particle momentum to 0, that's the infinite divergence. Right? If you leave aside that region, right, for example, usual scattering, right, you will never be on the threshold.
Oh, so we'll just keep k generic.
Exactly. We will just keep k generic. K generic means k non-zero. Right?
Right.
You don't have to take.
So there is no m square equal to 0 pole.
Exactly. Unless all the k's are 0. Right? Which is not a very good scattering problem. Right? So, unless all the k's are 0, you don't have this divergence for massless threshold. And that basically is related to the fact that the massless particles cannot decay into anything. That's why they don't get imaginary parts. Whenever you can adjust your external momentum to be on the pole, that means the reverse process is also true. That these particles can decay into these external states. Right? And that's why it shows that whenever you can actually sit on the pole gets shifted to imaginary by picking an imaginary part, okay, at loop order. Anyway, so this was just an aside to show the utility of having a field theory. Okay, that it's not just that you want to give a meaning to analytic continuation, but also field theory techniques can be useful in giving proper interpretation of what we compute in string theory. Now, a few points here. One thing is that you consider these two 3-point functions. We try to interpret this. I have erased it still there. Yeah. That if you look at these two vortices, they look symmetric, right? They are the same vortex after all. But the way they appear doesn't look completely symmetric because here the vacuum is on the right hand side, here the vacuum is on the left hand side. They don't look completely symmetric. So you have to somehow manipulate them to make it look symmetric. Okay, it's not a very deep problem, it's a trivial problem, but it is something you should do. Because if you want to give a field theory interpretation, it's better with the vortexes. These two vortices are exactly identical. Okay, you shouldn't have these kind of issues. But more important point is that this intermediate state that we see, this sum over n, okay, and this n, these are not on-shell states. You have to sum over all possible states in the basis. Okay. You cannot restrict to on-shell states in having a complete set of basis states. Okay, because you are keeping momentum fixed and summing over all oscillator levels, right? So it's off-shell. So clearly, to make sense of this, you have to deal with off-shell states at some point, right? Field theory doesn't work at purely on-shell basis, right? At least the intermediate states are on-shell, are off-shell. So for this reason, you have to try to understand, if you are really trying to reformulate string perturbation theory as a field theory, we have to learn how to deal with off-shell external states. Okay, so this is what I will describe now. Okay. And the reason that I am doing this, okay, I mean, one possible approach would have been to first describe the full on-shell methods, okay, the on-shell amplitude, and then show how to generalize it to off-shell external states. But we will see that the procedure that one requires for defining the full off-shell amplitude at arbitrary loop order, okay, is very close to on-shell amplitude. So you might as well do both of them together. Okay. So first I will introduce the notion of what the kind of thing that we need for off-shell amplitudes, and then maybe tomorrow I will give a general definition of how to construct off-shell amplitudes in string theory. Okay, and then the eventual goal will be to try to reinterpret that off-shell amplitude in the field theoretic language. Okay, as coming from some final diagrams. Now, off-shell for us will mean that it is a generic state in the Hilbert space, right? Not a primary necessarily. Okay, certainly not dimension 0 primary, not BRC invariant, finite. Then there are various restrictions you can put, okay, but right now we are not going to put any restrictions. So, general off-shell state, off-shell with no constant. In fact, we will see that this is not completely true. Okay, in the sphere you can get away with it, but eventually we will need to put some constant. So let me write it anyway. Eventually, we need that. Otherwise, you cannot really define option. Okay, so you keep this in mind. Once you go beyond the sphere level, you have to impose these conditions. But right now, let's just proceed with this. So let us consider a 3-point function. I1 of Z1, length. And in for a conformal field theory, the 3-point function is completely fixed up to the overall constant. Okay? Whether it is primary or secondary, it doesn't matter. But let's suppose that these are primaries. For primaries. Okay, because I'm just trying to illustrate what. Okay, so for primary one knows basically what the result is. Okay, then it closed form. Right, so it's some constant c times z1 minus z2 to the power h3 minus h1 minus h2 z1 minus z3 h2 minus h1 minus h3 z2 minus z3 times complex conjugate. Right? The complex conjugate basically means that all the z's are replaced by z bars and h's are replaced by h bars. Now, one thing to notice is that this depends on the choice of z's. Right? In particular, if you make an SL to C transformation, which is supposed to be symmetry of the vacuum, right? Not z goes to az plus b over cz plus b is not an invariance. And physically one understands why you are lacking this invariance. Because after all, this answer that you have written, it's understood that it's computed in a metric that is flat in the z coordinate. Right? It's computed in a metric which is dz mod square. If we make a change of variables like this, so the original dz mod square becomes dz over cz plus d square mod square. Okay. This, if I have done this, just simple exercise check. Oh, I should have said that here AD minus BC is 1. Okay. This is an SABC transformation, so it's AD minus BC is 1. Okay. So the metric changes. And it is because the metric has changed and these are not dimension 0 primaries that the correlation function is not invariant. Okay, because there is a Hall factor. And the metric has picked up some additional factors and that's what is responsible for the correlation function not being invariant. Okay, so even though it's not invariant, okay, one expects that there should be some remnant of the original invariance of the theory, okay, and in the following sense. Okay. So what is not invariant are the vertex operators. These are not invariant. Okay. But the theory is invariant. Right? Theory is invariant because you have taken total centers that equal to 0. Right? So on the conformal transformation, even though there is a while factor, there is nothing wrong with the theory. The theory is perfectly invariant under this. So in some sense it should be possible to make it manifest that the lack of invariance is because of these vertex operators and not and lack of invariance of the theory itself. In other words, the result for this, it depends on the choice of metric, it's correct, but it should depend on the choice of metric only around z1, z2 and z3. If you chosen the same metric around z1, z2 and z3, but change the metric elsewhere on the manifold, the result will be the same. Right? Because changing the metric elsewhere on the manifold is a genuine symmetry of the theory because the theory has a while invariance, right? It has total centers are equal to 0. So the question is, how can you make it manifest? That in the way I have written this, you cannot separate out the dependence on the vertex operators, the dependence that is coming because of the vertex operators, the whole manifold, because the metric is chosen once and for all as mod dz square, and that's what determines also the metric near the vertex operators. So what we want to do now is to use a formulation where independently you can choose a metric on the whole manifold, but the metric near the vertex operators can be adjusted independently. Okay, and I'll explain what one means by this.
So, any given point for one given point, it can be always shown that we can by transformation we can make it locally flat.
Yes, but that transformation.
The same transformation for all these three.
No, what I'm saying is that suppose we make a transformation that changes the metric away from Z1, Z2 and Z3.
Okay.
If you could do that, right? Then that shouldn't change the result. Okay, but the way I have formulated it, it's not possible to do that, right? Because as you make the transformation, you also change Z1, Z2 and Z3, right? And SL2C transformation, you move around Z1, Z2 and Z3, right? So you have to find a way to make it manifest that dependence, the reason that it depends on Z1, Z2 and Z3 is because the choice of metric near the vertex operators is changing, not that the metric everywhere else is changing. Is this clear? Okay, so what one does to make it manifest is to use the notion of local coordinates. Local coordinates near punctures. Punctures, okay, is a technical word. These just are the points where the vertex operators are. So what this means that you have these 3 points here. Around this point, you choose some coordinate system W1. Around this point, you choose some coordinate system W2, and around this point, choose some coordinate system W3. And it is useful to choose the W in such a way that W1 equal to 0 or W1 equal to 0 is location of ith function. Okay, it is not necessary, but it's useful to do this, and we will be using this convention that in the local coordinate associated with the function is at origin. Then you have a coordinate system Z that describes the sphere that on a plane. Okay, that's independent of the W's. But of course, there should be a functional relationship between Z and W. Okay, because after all, it's a point here is can be either described in the W coordinates or in the Z coordinate. So they should be related. So there are some functions which relate Z to W. Is this clear so far? Right now, all I am doing is choosing coordinates. Right? Instead of using one coordinate system, right, I am saying that there is a overall coordinate system Z that we will be using. That's a plane in terms of which its length is the whole plane. And then there are some local coordinates W1, W2, and W3 that I am choosing right, around each function independently of Z. Okay, but there is a functional relationship. Okay, if I encode that functional relationship. Now the idea is that we insert the vertex operators in a metric that is not mod dz square, but mod dwi square. Okay, so here, close to w1 equal to 0, the metric that you choose for inserting the vertex operator is mod dw1 square. Okay, we say the vertex operator is being inserted in the coordinate system w. Okay, that basically means that the metric that you have chosen is mod W square. Similarly, you insert the vertex operator, second vertex operator here in the coordinate system W2. Okay, which means that you choose the metric here to be mod W2 square and similarly mod W3 square. Is this clear? And then you want to calculate the correlation function. Okay, in the plane. Okay, you have chosen the vertex operators phi 1, phi 2, or phi 3 in the coordinate systems W1, W2, W3, and you want to know how to write down the correlation function in the whole plane. So now to find the correlation function in the plane, we have to first know how the vertex operator transforms as you go from W to Z coordinate. Right? Because you want to rewrite this vertex operator that we inserted in the W coordinate in the Z coordinate system. And then you can calculate the correlation function because you have a general formula for the correlation function if you have inserted in the Z coordinate system. Right? This is the formula that we will be using. But first you have to convert from the W to Z coordinate system. Is this clear? And the general structure. So, if Z equal to f of W, then the vertex operator, the operator, the local operator phi, in W coordinate system appears as some operation on phi, f dot phi, in the Z coordinate system. Okay, we will explain what f dot phi is. Okay, f dot phi is a general notation that transforms the function from W to Z. Okay, if Z is f of W, okay, then f dot phi by definition is something that transforms from W to Z, so that then we can insert it in this formula.
So by this choice that the insertions will be at the 0 of the local coordinates,
Yes.
and also the metric at the local coordinates are flat. Like
Yes.
that means I am choosing some Z to be a phi wi near the context.
Yes.
Am I exhausting all the coordinate choices that I have there, or there are some?
Well, we are not exhausting all possible choice of the metric because we are assuming that the metric has still the form of holomorphic times an anti-holomorphic, right? You could consider metrics which are not a holomorphic function. See, this mod dz square and mod dw square, that will still be related by product of holomorphic and anti-holomorphic function. Right? That is not the most general choice of the file. Okay, but we will be working within this class of metrics. Okay, there are more general choices, but we will not worry about those choices.
So ultimately my result should depend on this f and phi and not these w's and z's.
Yes, ultimately it should depend on the z's. That's the point. Okay, we'll see how that happens. Oh, I should have said this. So this basically means that fi of 0 is there. And we have punctured, ith puncture is located at wi equal to 0, right? But in the z coordinate it's at zi. That was the definition, right? So zi is fi of 0. So let's look at examples. What is f dot phi? Right? Then it will become clear. So if, for example, phi is a primary of dimension h bar h, then f dot phi of w is f prime of w to the power h, f prime of w bar to the power h bar, and phi of f of w, f of w. Okay, so this is what you get in the z coordinate system. So if phi was a dimension 0 primary, right, then it will be invariant, which basically means that f dot phi of w will be basically phi evaluated at f of w. Yeah, the new z coordinates. Yeah, you are just changing w coordinate to z coordinate. But if phi is in general a primary of non-trivial dimension, then you will pick up extra factors here because of this transformation. If phi is not a primary, it's a secondary, right, then there will be additional terms. There will be additional terms in the secondaries. For example, if this was an energy moment tensor, there will also be additional terms which involve this Schwarzschild, right? Energy momentum tensor really transforms under conformal transformation. Right? It has not only this part will of course be there, right? But it has additional pieces, right, which reflect the fact that it's not a primary of conformal. So for any field, any local operator, knowing how it transforms, how aliens act on the local operator, you can figure out what this sign is. Okay, you basically have to integrate the differential equation and figure this out. Okay, the important point is that there is always some thing on the right hand side that you can explicitly write down. Right? That's what I mean by this symbol, the f dot phi of w. Okay, I just gave the example of a primary because it's easy to write down. Is this point clear? Okay, so if you insert phi's in the local coordinate system, that is the w coordinate system, then the correlation function on the sphere has to be written as f1 dot phi 1 of 0, f2 dot phi 2 of 0, f3 dot phi 3 of 0. Okay, because what we have done is we have inserted phi 1, phi 2 and phi 3 in the w coordinate system at w1 equal to 0, w2 equal to 0 and w3 equal to 0. Okay. But to calculate the correlation function, you know the result from the z coordinate system, so you have to convert it back to z coordinate system and then calculate it. Okay. And these, how to convert it is given in these rules. If phi is primary. Okay. If phi is secondary, there are more complicated rules that you have to use. Okay, but let's consider the case where phi is primary. So this is given by, we can use the formula explicitly. f1 prime of 0, let me write this as product, f1 prime of 0 to the power h I, f5 prime of 0 bar to the power h I bar, and then phi of f1 0, phi 1 of f1 0, phi 2 of f2 0, phi 3 of f2 0.
If dot phi is like the operator in the z coordinate system.
Yes, that's it.
So the argument is
Well, so this is just notation. The argument is that of phi. Once you transform it, it becomes, here you can see the argument has changed to f1 of 0. And this is a z coordinate system. So that's just a matter of notation, right? So f dot phi of 0, this argument is in the w coordinate system. And then here it becomes in the z coordinate system.
This is like the del z del w vector.
This is, yes, that's right. So these terms are like del w, del z, del w to the h terms, exactly. And now what is the claim? Okay. The claim is that this result should remain unchanged if you have made a change of coordinates of z. It does depend on the choice of w. Right? If you change, for example, w1 to something else, the function f1 will change. Right? If you keep z fixed and change w1 to a different coordinate system, f1 will change. And the result should depend on that. choice, okay, which you can clearly see. Okay? If we just change f1 arbitrarily, this is not going to remain invalid. Right? If we replace f1 by f1 tilde, the result will change. But you have to make sure that this now is independent of z. How you have chosen the global coordinate system on the plane. And you can make a SL2C transformation on z, and the result should be unchanged. Is this point clear? So, the claim that the result should be unchanged. Z goes to z plus b for c plus d. Okay, so we'll now check that. So Z and W are related parties. Yes, right? So if you keep the Wi as fixed and change Z by transformation like this, these functions will change. Right? So Fi will become Afi plus B over Cfi plus D.
So does this mean that I am changing Z, but also demanding that the function should be at the zero of the local coordinate still, like even after doing the SL2C?
Well, SL2C is acting on the Z. It has nothing to do with W's. So what you are doing is that you are changing the coordinate system on the sphere. Right? The W's are remaining unchanged. Right? The punctures are of course fixed. Right? In the W coordinates. That you are not changing. Right? You are just re-labeling what you are calling Z1 earlier has become something
The
else.
map from Z to W is changing.
Exactly. The map from Z to W is changing and that's fixed. The punctures are still at W1 equal to 0, W2 equal to 0, W3 equal to 0. The matrix that you are choosing is dW1 square, dW2 square, and dW2 square, dW3 square near the three functions. All that is changing is the relationship between Z and W because Z has changed.
Map from W to Z, right? Not Z to W.
W to Z. Given a point in W, this tells you what the point in the Z coordinate is. But near the local coordinate, it should be one-to-one map. Near W, right? So this Fi of Wi should have a branch point at Wi equal to 0, for example. Right? Then this map is irrelevant. Okay, so so this is a statement, and now we can easily check this, right? Whether this is true or not. Okay? But to check this, you have to remember that this function is Fi minus, let me write it as F1 minus F2 to the power H3 minus H1 minus H2. F1 minus F3 to the power H2 minus H1 minus H3 and F2 minus F3 to the power H1 minus H2 minus H3. Transform this complete. So the question is, this combination, does it remain invariant under a transformation like this? Earlier, what we have checked, what was not invariant, we didn't have these factors. Right? Otherwise, it was similar to this f star plus x. This was not invariant, but now we have to check if we including these factors, this does become invariant under this transformation. And one can easily check that this is true using the following relation. So Fi prime, in fact, you can show this is exercise. Fi prime goes to Fi prime over Cfi plus b square, and fi minus fj goes to fi minus fj over cfi plus d times cfj plus d. Okay, this you can easily check from there. Okay, and you have to of course use the fact that AD minus BC equal to 1. And once you use this transformation law, you will find that indeed all the extra factors that come from here, we cancel the factors that come from here. And this correlation function is indeed invariant under the change of z coordinate system.
In general, in a CFT, isn't it natural to say that if you do a conformal transformation, the phi will go to some phi prime, which will pick up the scaling that of the weight of the phi prime, and then you fix the denominator z such that the whole correlator is invariant? Isn't it a normal thing?
Yeah, it's a normal thing, but the point is that suppose you want to define the offset amplitude. Right? There you are not changing anything. Right? You have phi 1 of z1, phi 2 of z2, phi 3 of z3. It depends on z1, z2, z3. Right? So now you have to characterize what that dependence. Right? Offset amplitudes are not independent of the choice of the local coordinate system. Right? So what this is allowing you to do is to characterize the dependence. Offset amplitudes are dependent on something. Right? It's not like on-cell amplitudes, which are independent of the choice of coordinate system altogether. Off-cell amplitudes will depend on the choice of coordinate system. But what this is saying is a way to characterize that dependence by identifying that it depends on the choice of local coordinates around each function, but not on the global coordinate on the surface. Right? So what you are saying is that if you make a combined transformation of a field, you change the coordinates as well as you take into account the scale transformation of the fields, then of course by definition the whole thing is invariant. Right? But we are not transforming anything here. Right? If you just take the fields that as z1, z2, z3, right? And suppose you don't know anything about the fields, you want to now calculate the offset amplitude and you change your coordinate system, right? The result will change. Right? Because what is telling us that you should transform phi, right? Phi are given once and for all. So the offset amplitude will depend on the choice of coordinate system. Is that point clear? See, phi's are given as states once and for all. Right? You are not trying to change your phi's. Right? You have to define the offset amplitude for these states. And what I am saying is that when you try to define the offset amplitude for these states, you have to fix some z to z, the value fix them. Offset amplitudes do depend on the choice. Right? And you have to find a way to characterize that dependence. Right? Well, eventually you want to show that the physical quantities are independent of any such arbitrary choice, but the offset amplitudes do depend on that choice. And what you see from here is that the actual dependence of the offset amplitude can be encoded in the choice of the w's. See here, once you have written it in this way, right, you are not transforming the phi's at all. Right? This result, this combination, is the definition of the offset amplitude of the phi's. And now you are saying that we just change z. Right? We are not transforming phi's. We change z to az plus b over z plus d. Consequently, the phi's will get changed, but the result is invariant. Right? You are not we are not transforming the phi's at all. Right? These phi's are not transformation functions. These phi's are given once and for all to us. So that's part of the definition of the offset amplitude. Is that point clear? Right? We are not looking for a symmetry of the square. Right? We are trying to find a way to define the offset amplitude in a way that is independent of the choice of coordinate system on the plane. And what we have managed is that we have achieved that it's independent of the choice of coordinate system in the plane. If we just change z to z plus p over z plus d, the result is indeed unchanged. However, the definition of the offset amplitude depends on the choice of coordinate system around the functions.
That is the f levels.
That is the W's. Right? The W and W, so the function F encodes essentially W's. Right? If you change W, then the result will change. Okay, see that you can change F either by changing Z or by changing W. These are two different kinds of changes. Changing Z changes all the F's simultaneously, right? Because Z is a coordinate system on the whole very one surface. W's you can change individually. If you change any of the W's, the result will change. Which basically shows that the axial amplitude does depend on the choice of local coordinates.
Like the VLY from
It's like, well, I don't know.
local, there will also be defined.
Yeah, so in that sense, yes. I mean, you think of it as a local frame.
Unless we do any rotation in that.
Exactly. Yeah. That you can always define frames in such a way that it depends on a local frame.
Yes.
Right? But on a general coordinate transform, it transforms the scalar.
Yes.
Yeah. Is this point clear? So this will be a general thing that to choose the definition of the axial amplitude will require that we choose some specific local coordinates at the punctures. Changing the local coordinates will change the definition of the axial amplitude. Okay, but the dependence is in the choice of local coordinates. Okay, it is possible to change the coordinate system on the Riemann surface. Okay, and as long as you keep the local coordinates unchanged, okay, changing coordinate system on the Riemann surface is not going to change the amplitude. But if you didn't distinguish between this choice of local coordinates and choice of the global coordinate, then it would look like that the result depends on the choice of coordinate system on the Riemann surface. Okay, unless we separate out the dependence on W from the dependence on Z, right? Everything seems to depend on Z, right? Because earlier we have chosen the W's to be equal to Z's, right? And that's why you couldn't see the fact that the result really depends on the choice how you have chosen the coordinates near the punctures and not on the overall choice of the coordinate system.
So is it equivalent to say that if I don't want to consider W, I have a Z coordinate system on the full sphere and I have insertions at Z1, Z2, Z3.
Yes.
So numbers 1, 2, 3.
Exactly.
And I do a change in Z, but physical point which was previously Z equal to 1 is still Z prime equal to 1,
Yes.
Z prime equal to 2 and Z prime equal to 3. Then and if I use a 3-point, I compute a 3-point function with those these are the
But if you make an SL to C transformation, right? It is impossible to fix these 3 points.
Oh, sorry.
Right? You cannot keep them at the same point, right? So the Fi of W are typically not SL to C transforms, right? These kind of branch cuts outside some disk, right? All you are demanding for the W's is that around the function, it should describe the space in a one-to-one fashion. Is this, yeah? Right? For example, you could have taken the Fi's to be SL to C transformations, but different SL to C transformations are on different functions. Right? That's perfectly allowed in this comparison.
As long as I keep my W's unchanged, the electricity is locally flat around.
Exactly. Because by definition, this correlation function that we talked about, this one, right? This one is interpreted as the correlation function calculated with the metric chosen to be dwi mod square around the ith function. Okay, and that's the reason why changing the z coordinate system is not affecting this correlation function.
For on-shell states, we expect that this choice of W should not matter, right?
No, yeah, exactly. Because on-shell states these are all 1. H and H bar are all 0. Right? So for on-shell states it is true that if you change W, the result will value change. Right? There is no dependence on Fi's. So the dependence on W will come from off-shell states. For off-shell states. Okay, on-shell states are independent of the choice of Z as well as choice of W. Okay, maybe I just end by describing the VPZ conjugate because once we have introduced the notation, it's easy. So we had defined earlier the state operator correspondence, right? Phi is phi of 0 acting on vacuum. Now we define dpz conjugate. Phi, which is where I of z is minus 1 over z. Okay, or maybe let's bring it as w. Doesn't matter actually. It's a function. So let's see what it means for primary. So for primary, I of phi of w is what is it? I prime of w to the power h times complex conjugate times phi of I of w, right?
Yeah.
So this I prime of w is 1 over w square. So this gives you w to the minus 2h, w dot to the minus 2h bar, and then phi of minus 1 over w minus 1 over w bar. So what this says is that for a primary, phi is given by limit w goes to 0.
This basically keeps the inner product defined, right? So this is the phi Hermitian that we normally.
This is not the usual Hermitian conjugate necessarily.
No, in CFT we define this. I don't know the name, but this is the usual.
Yeah, so this basically says that phi with psi is given by I dot phi of 0. So it's the vacuum expression value of I dot phi of 0. Psi of 0 on vacuum, right? Right? Because I of this is phi and this is psi. And this I can write as a correlation function. Without any reference to states, you can define if you have two operators, psi and phi, their inner product, okay, which is a BPZ inner product, is given by this. Okay? So written in this language, you don't write the states at all, right? This is just given in the multiple function. But I should, so this is a general definition. Okay? This is spatial. This is spatial for primaries. If phi had been secondary, then this would be more complicated. Nevertheless, this definition is always there. Right? This is the standard. This definition will take as the standard definition of what we mean by the kth vector phi.
How to understand this omega goes to 0 limit?
Oh, because the correlation function, this when you insert in the correlation function, right, you will always get a finite answer. Because the correlation function of a conformal operator of conformal dimension h, right, falls off as z to the minus 2h as z goes to infinity, right? So that will exactly cancel these terms. So this conformal transform is a useful notation even without worrying about official states. And that's why I thought I'll write it here. So this is the definition of the BPC inner product involves the conformal transformation, but with this very specific operator I, the specific function I. So where I basically is something that maps from 0 to infinity. Okay, so I think I'll stop here and then
continuous mode.